everyone, good morning. I hope you guys had a great day yesterday. A couple of things. Class is not going to be very, very long because of the nature of the activity. And we do not have a scheduled class tomorrow. The reason we don't have a scheduled class is because the activity that we're scheduled to do tomorrow, I have to record. It has to be done outside. And I have to probably switch locations because I'm going to need the use of sunlight. So I'm going to do a traditional YouTube video that you guys are accustomed to me doing from earlier in the year. I'll record the class outside and bring it into the house so that you're able to view what it is that you need to view. So no scheduled class tomorrow. The video will be uploaded hopefully in the morning. I may or may not do it tomorrow. I have to look at tomorrow's weather. In order for me to actually do the video, I have to have sunlight. So if it's too cloudy, I won't be able to do it. I may do it this afternoon if I can do it in front of my house tomorrow. If not, I'm going to have to do it in my yard or in front of my house today because the sun is moving. If not, I'll have to do it in my yard tomorrow. So we shall see what has to be done. And I will let you know. Okay, so I'll post in Edsby. Once I do have the video uploaded, I'll post in Edsby and remind and on our Science with Mama J Instagram page that I have posted the video. Also, wanted to give you some quick information. I have begun emailing. Now, Edsby's a little on the slow side today, so it's taking me a little bit longer, plus my emails are individualized. So if I haven't emailed you yet, but you received a 0 on an assignment, please go in and do the assignment. If you can't do it for whatever reason, if my system didn't put the assignment back in for you to do it, please let me know and I'll fix it. I will not be grading anything until I've emailed every single student. And the reason for that is because I want to make sure everyone knows what they're missing. Once everyone's emailed, I'll go back in and start grading. So if you turn something in, please be patient. As soon as I'm done emailing everyone, I'll start grading. Now, if it takes me the rest of the afternoon to email, I'll start grading tomorrow morning. If not, I'll start grading today. But please, please be patient. Also, we are coming down the home stretch. We're doing activity 93 today, and I will be recording activity 94 tomorrow. After that, we've got 5 sessions left and we're done. So you'll be given the opportunity to have time solely for makeup work. No brand new assignments. I might host some, interesting classes, maybe in biology, since you guys will be taking it next year. They won't be mandatory. I'm not going to grade you on them, but it'll give you an opportunity to interact with your classmates, and it'll give you an opportunity to maybe learn something new and interesting. And if there's a particular topic you would like, I'm happy to do that. There may be some classes, because again, of the nature of the activity, that I won't be able to host a live class because I have to do it in sunlight and then bring it in. I know there's at least 2 like that. So our classes are down to 5 or less, just so you know. We'll talk about when we get closer to the end what we're going to do once classes are over, in terms of maybe giving you guys some time to interact. Since I'm thinking about it, I'm formulating it. If you want to throw some ideas at me, feel free to email me or post it on the page. I am thinking I may do kind of like a spirit week type of thing, where maybe if we're good, we'll meet up in a Zoom session, small sessions where you guys can interact with each other. Don't know yet. Kind of trying to figure out what we could do, but it is contingent. Well, video, talking, you guys interact a little bit with each other here. It is contingent on good behavior. So if someone is acting up, if they're saying something inappropriate, if something inappropriate is on video, you're booted out of the session and not going to be allowed back in. So more details on that to come once we get to, once we cross that bridge. So the next test will be, as far as I can tell, I don't have my paperwork in front of me. I think there's only one test in Unit F, and it's at the end. I will verify that and I'll let you know, but I believe it is at the end. Okay, so let's look at the nature of waves. Okay, this is a reading, which I'm going to go through the reading with you for a couple of reasons. Number one, some of you have issues getting in, opening documents in EDSB and getting into your online textbook. Number two, I want to be able to go through it with you. That way, if there's anything that needs explaining, I can go over it. So, sound is only one of several kinds of waves. Some waves carry a small amount of energy, such as the waves you observe in the long coil on the floor, a whisper, or gentle water waves. Other waves transfer a tremendous amount of energy, such as the energy transferred in earthquakes, tsunamis, or gamma waves. There are waves that humans cannot detect directly, even though some of them carry a lot of energy. In this activity, you'll learn more about the various kinds of waves. You will also learn how certain devices extend human sensory capabilities. Okay, so some waves you see, like water waves. I have my son behind the camera making funny faces. So if I laugh, you know why. Some waves you can't see, like electromagnetic spectrum waves. For example, X-ray machines, microwaves, radio waves, all of those are producing various types of waves. And they're electromagnetic waves, but you can't see them, okay? In some cases, you may feel their effects. While you feel the effect of a radio wave, you can hear the sound and you can feel the vibration, okay? But when it comes to something like, that makes a lot of noise on the camera. We noticed it yesterday. It makes a lot of noise on the camera. So something like radio waves, you hear the sound. Now, X-rays, you don't feel it, but if you were to sit in front of an X-ray machine and have someone repeatedly take X-rays, it could actually begin to burn. Okay, so no matter what kind of wave or what amount of energy it transmits, it is important to note that when waves transmit energy, the individual molecules or particles in the medium are not transmitted. In other words, a medium does not move along with the wave. A medium, or plural media, is the material in which a wave energy transfers. So, for example, the air is a type of medium. Space is a type of medium. Water is a type of medium. The solid it's transferring through is a type of medium. Okay, so mechanical waves such as seismic waves move through the ground, water, air, and other materials. For example, when making waves in the long metal spring in activity 91 longitudinal and transverse waves, the metal in the spring was the medium. The disturbance moved away from the source. The coils of the spring temporarily moved up and down or closer together and further apart, but the spring did not undergo a permanent change of position relative to the source. In this case, the medium itself, the metal of the spring, was not transferred from the wave maker to the other end. So I would have used the spring, but I think my son stole it. So when you saw me hold the spring, okay, you saw me let go and energy transferred, but the spring itself still stayed in position and did not move. Okay, water, and you're not probably going to have a hard time believing this, but as energy is transferred through the water, you'll notice something can bob up and down in the water and stay relatively in the same position. That's because the water itself is not displacing, the energy is displacing. Okay, so as energy is moving through the water, it itself is being displaced, but the water is staying relatively in place. Okay, so what is the medium for an ocean wave? Provide evidence that the medium is not transferred when water moves on a lake. I'm sorry, I didn't even know that was there when I mentioned the water. So in activity 91 longitudinal transverse waves, you investigated two fundamentally different types of waves, longitudinal and transverse. A longitudinal wave is one that transfers energy through compression and rarefaction in the medium through which the wave travels, and sound is an example of a longitudinal wave. When you hear a sound wave through the air, you are detecting a disturbance in the pressure of the air. When the air pressure is increased, air molecules are being pushed together into a compression. When the pressure is reduced and the air molecules move further apart, it is a rarefaction. A longitudinal wave is one that causes the medium to move parallel in the direction of transmission or the propagation of a wave. So I'm speaking to you. My voice is traveling through the microphone. The air between me and the microphone is being compressed and then refracted. Okay, so compression and then release. And that's how the sound wave is traveling to you, because I believe I mentioned this in the classroom. Energy in a bucket, when you're putting out a fire, you take the bucket and the bucket goes from one person to another person to another person. Sound is traveling on the particles in the air like that, okay? Which is also why sound travels better in a closer medium than a medium that's more expanded. For example, sound will travel better through a solid than through a liquid, and it'll transfer better through a liquid than through gas, so better through water. What are you doing? It'll transfer through water and better than air, and sound can't travel through space at all. So if you could suspend disbelief for a moment and stand in front of someone, they could literally be this close to you, but there is nothing touching. If you were to scream as loud as possible, the person directly in front of you would not hear you, because there is nothing to transmit the sound from you to that person. Okay? So, a transverse wave that travels through a medium is a result of the medium moving perpendicular to the propagation, to the direction of propagation, The long coil used in the previous activity was an example of a transverse wave. So light is another example of a transverse wave. So, for example, particle motion is like this in a transverse wave, okay? He brought the slinky back. Okay, so particle motion in a transverse wave is like this. So the particles, as you can see, the slinky is moving straight up and down, okay? All right, so in that particular case, as the slinky is moving up and down, okay, the wave itself is moving to, in this case, my right, okay? So, and when I post on EDSB, there's a picture that discusses direction of wave movement and wave propagation. So you'll be able to see that. Direction of particle movement and wave propagation. So how is a transverse wave different from a longitudinal wave? Mechanical waves, such as earthquakes, sound waves, or waves in a coil, will travel differently depending on the medium. The same wave will travel at different speeds through different substances. In general, waves travel faster through materials that have springier molecules and bonds. This means sound moves faster through solids and liquids and faster through liquids and gases. For example, sound travels about 5 times faster through metal than through air. Okay, so if you have someone who is banging on a wall and you happen to be laying in your bed next to that wall and your bed is touching the wall, covering your head with a pillow is not going to help numb the sound that much, because it's going to travel directly to you anyway. Because sound waves always involve the physical disturbance of atoms or molecules, they are referred to as mechanical waves. A mechanical wave must have a medium in order to travel. Mechanical waves cannot travel through a vacuum because there are no atoms or particles in a vacuum. Although outer space is not a perfect vacuum, the molecules are so far apart they do not allow the production of compressions and rarefactions, and therefore sound cannot travel in space. So that's basically what I just finished telling you. You would not be able to, that's kind of funny, Esteban. They would not be able to hear you because the particles are so far apart, they can't move sound waves. For example, remember the bucket and the fire. If you're standing 10 feet apart from someone, unless you were to walk from point A to point B, you would not be able to hand them the bucket. So you would not be able to put that fire out. So if you were a particle, you're not walking, the particles aren't necessarily moving, or they're not moving further along enough, you're unable to transfer. Okay, hopefully that analogy helps make a little bit more sense. Some waves, however, do not require a medium and therefore can be transmitted through a vacuum. For example, light travels through the vacuum of outer space where sound does not exist. Because light waves do not require the presence of atoms or molecules, they are not considered to be mechanical waves. Light is a transverse wave that carries electromagnetic energy, so something I spoke about a few minutes ago. This energy in light waves travels about 900,000 times faster than energy carried by sound waves. Wave speed. So energy has 4 basic characteristics. Some of them we've already talked about. You have frequency, okay, or how fast a wavelength, or how fast the wave moves, basically how many waves pass through a particular distance within a given amount of time. Wavelength, okay, we talked about wavelength before, but what is the distance from one point on a wave to that exact same point on the next wave? Okay. Amplitude. The amplitude is the height from the disturbance to the top, or in the case of the trough, the bottom of the wave. And the last one is speed. Wave speed measured in meters per second is the distance traveled by a certain feature of the wave, such as a crest, in a given amount of time. The speed at which the wave travels depends on what type of material it transfers through. Sound is transmitted through the air about 340 meters per second. That exact speed depends on such factors as temperature and humidity of the air. The tables on the next page show the speed of the sound and the light through various media. Although light slows down a little bit in air, it still travels about 900 times faster than sound. That is why you will see a lightning flash long before you hear the sound of thunder from a storm several miles away. And if you see a lightning flash, it tells you about how close it is, because the closer the lightning flashes to your location, the faster you will hear the thunderclap following the lightning flash. So if you hear a lightning flash, and if you see a lightning flash, excuse me, and then about 5 seconds later, you hear the thunderclap, then that lightning strike was much further than if you see the lightning flash and only hear about 2 seconds later the thunderclap. That lightning flash was much, much closer. Okay? So, what does it mean if you hear thunder and see lightning almost at the same time then? So if you almost can't distinguish the thunder and the lightning difference, what does that mean? I'll give you guys a second to answer. Run. Rosie said you're next to it. Esteban said run. Esteban, that's a good answer. Okay, but yes, Rosie, you are correct. Well, if you just got struck by lightning, then you're clearly not going to be able to run. But it means that that lightning strike was very, very close. Now, chances are it is also extremely loud. And it may even produce a wave that will almost shake your house. Okay, we've experienced those a few times. Okay, so, okay, and I've got a couple of your deads, and rest in peace. That's kind of funny. All right, so although our world is full of sights and sounds and waves, there are many sensory organs that cannot detect directly, that many waves our sensory organs cannot detect directly. However, people have invented devices to detect waves having frequencies that fall out of our range of hearing and vision. These devices include cell phones, radios, X-ray, film, radar, and sonar. Each of these devices receives energy from a wave we cannot detect and it converts it into something that we can see or hear. So cell phones, obviously, they detect sound waves, radio waves, sound waves again. Okay, X-ray film will actually detect radiation, okay, X radiation, okay. Radar and sonar. Sonar is sound waves. A radar, I believe, I'm not 100% sure, is either a light or a sound. We use radars for different things. I believe radars pick up certain sound waves. I know sonars tend to use sound waves underwater or under the earth. So, oh, here we go. Radar tends to work by sending radio waves. It is a radio wave, okay, from a radar source to the surface of a target, such as an airplane or a cloud. So radars tend to work above ground. The waves are reflected back to the radar source, and the location of speed or target is calculated from the measurements. So a radar then will detect how far something is or how fast something is moving based on how fast the light travels or the sound travels and how fast it comes back. The waves are reflected back from the radar source and location speed started based from the measurements. Radar systems are based on radio waves or microwaves. Sonar works in a similar way, but relies on sound waves at frequencies that are not detectable by human ears. Sonar allows personnel on ships and submarines to detect depth of water and the pressure or in the presence of fish and other boats in the underwater surface. Seismic waves are low frequency mechanical waves that move through the earth. They are caused by such events as explosions and earthquakes. By measuring seismic waves with a seismograph, even those waves that are not felt by humans or on the surface of the earth, scientists locate earthquake epicenters and create maps showing regions at risk of earthquakes. All of these are examples illustrate in ways. Okay, let's try that sentence again. All of these examples illustrate ways in which people have invented devices to employ the energy of waves to hear things we wouldn't normally hear and to see things we normally would not see. So hopefully that helped you get an understanding of waves and what we use them for. I will be posting questions. I know I still have to post questions from the other two. I was just trying to get those emails out. And I also have a quiz that I'm going to post. It's those of you who were here, you are already paying attention. Those of you who have not watched the video yet, you may want to encourage your friends to watch the video. Or if you logged in late and missed part of it, I would encourage your friends to watch it because we want to make sure that you see it before taking that quiz, because it's a quiz based on things I've said in the video. Okay, if you have any questions, please feel free to let me know. Remember, there is no formal class tomorrow. I will do a recording and post the recording on Edsby. Otherwise, unless you have any questions, that's pretty much it. And I look forward to seeing you guys really soon. Okay, I will post on Edsby if there's going to be a formal class on Thursday. I have to look at the activities for that. All right, take care, guys. I'll be on for a moment. No, thank you. I'll be on for a moment to take any questions that you may have. But otherwise, I'm going to go ahead and end the stream, and I hope you have a wonderful rest of the day. Bye.